So up until now we have not talked about friction, except maybe just in passing. But friction is ever present in our daily lives. So what is it? So imagine you're moving a box across a table. It may seem very smooth, but if you were to look at it at the atomic structure, really both surfaces are very, very rough. So it's almost like you're trying to move mountains past each other. And once you get it started moving, then it's a little bit easier. And that's because there's two types of friction. Friction is either static friction, which is the friction beginning at the beginning of motion, or kinetic friction, what's present once motion starts. And it turns out that static friction is always, always greater than kinetic friction. To find your friction acting on a surface, whether it's static or kinetic, you're going to use the formula friction equals mu, which is called the coefficient of friction, times the normal force. Remember that the normal force is not always the weight. It could be F perpendicular, it could be the weight plus some force or the weight minus some force, but it's not always the weight. So you have to really understand your vector diagram, your free body diagram for your situation to be able to plug in the right normal force. That mu is uh, um, is a coefficient, and it doesn't have any units. It just tells you the ratio of friction to normal force. So if the ratio is 1, that means the friction is equal to the normal force. If the ratio is 0.5, it means the friction is half of the normal force. If the ratio is 0.25, it means that the friction is 1/4 of the normal force. And so mu static and mu kinetic are going to be different because there's a different amount of static and kinetic friction for different surfaces. And it is a surface situation. It's like what kind of surface is in contact with another kind of surface. For example, um, Teflon on steel has very, very low coefficients, but rubber on dry concrete has a very high coefficient. Most of the time that will be given to you, and if it's not given to you, you'll have access to a table to look it up on. All right. So just remember there's no units and it's just a ratio. And that the lower the number, the smoother the surfaces are. All right, so let's just look at some free body diagrams and how we would draw um, those. So let's look at A, B, and C. So a book on a table. So for diagram A, so we've already talked about this, that if you have a book on a table and you are thinking about it, that it's pushing on the table with its weight and the weight is pushing back equal and opposite. So the normal force in this scenario is in fact equal to the weight of the object. Now, you're going to push it with an applied force, and if friction is in the system, friction always opposes that. So that's the difference. You just add friction opposing Fa. So when you look in the y direction, all of the forces balance each other out. So the normal force has to be equal to the weight force. And in the x direction, all the forces do not balance each other out because it's accelerating. And if that's the case, then we're going to, since it's a single mass system, we're just going to use right is positive, left is negative. It would be the applied force plus a negative FF or minus FF equals MA. And remember, FF is mu times Fn, and that's why it's important for you to know what Fn is equal to. If you don't know what that is, then you're in trouble. Look at a box or something on an incline plane. Okay, so for B, so remember we had our incline plane. It had weight, which is perpendicular. Oops, my bad. Weight, which is perpendicular to the floor. It had a perpendicular component of the weight and it had a parallel component to the weight. and it has a normal force. And now it has friction, and friction is going to oppose the direction of motion. So if it's sliding down the incline, friction would be in this direction. So in the y directions, all the forces are going to add up to 0, and in this case, that means that the normal force is equal to F perpendicular, which is mg cosine of the angle of the incline. And in the x direction, all the forces do not add up to 0, and it's going to accelerate. And we're just going to say the direction of motion is positive here. F parallel is positive, and FF is negative. So this would be F parallel minus the friction causes the mass to accelerate. F parallel is mg sine theta, and FF is mu Fn, ma, but in this case, Fn is F perpendicular. All right, so let's just look at a couple of examples. So let's say that we have 100 Newton box, and it takes 50 newtons to start it moving and 25 newtons to keep it moving at constant speed. So let's just talk about that. So we already know that our box is going to have weight, which is 100 newtons, and it's going to be balanced by the normal force, which is also 100 newtons, and that it has an applied force, and that it has a friction force acting on it. So what this is telling me is that to start moving, it's going to take 25 newtons to keep it going. Oh, I'm sorry. It's going to take 50 newtons to get it started. So we want to figure out the kinetic friction. So if it takes 50 newtons to start it, then that must be how much static friction it has. So to find the first one, I'm just going to use FF equals mu Fn, and mu is just going to be 50 newtons divided by 100 newtons, which is 0.500. So no units on that, because the static friction force is 50 newtons. The kinetic friction force is 25 newtons. So that is FF kinetic. And mu is going to be equal to the friction force divided by the normal force. 25 newtons divided by 100 newtons, 0.25. No units. So these are the coefficients, the decimals, and the actual forces are given to you in the problem.